The load diagram also prompts consideration of the definitions of limit load (LL) and ultimate load (UL). So typically, an aircraft operates near a load factor equal to 1. Okay, this line, load factor equal to 1. And its performance rarely approaches the limits of the flight envelope. So we said that the whole thing is called the flight envelope. Uh, the static design of a structure or component is primarily based on the limit load, LL, which represents a high load that occurs only once in the aircraft's lifetime, and all other loads experienced during the aircraft's lifespan are generally lower than this limit load. When the limit load is applied, the structure shouldn't sustain any remaining damage or deformation. And by multiplying the limit load by a safety factor, limit load times a safety factor, typically this safety factor is something around 1.5 or 2, we obtain the ultimate load then. And this ultimate load is the maximum load that a structure should be able to withstand for at least 3 seconds before its complete failure. And if the structure doesn't fail under the ultimate load, it may still incur damages or deformations. The load diagram and the definitions provided can also be corrected with the various materials utilized in aircraft construction. When examining the force and displacement curve of a metal alloy, actually you will see this kind of plots in your materials course, Science of Materials. There's a force in the y-axis and the displacement in the x-axis. So when you examine this curve for a metal, you observe both elastic and plastic behavior. So elastic means if you apply some force, you will see some displacement, but if you are in an elastic region, it means that if you just remove the force, it will come back to its first place. But if it is going to the plastic region, when you apply a higher force, you will have such a displacement that it cannot back to its uh, previous value. Uh, so you have some point called yield point, and the force that is applied, it's called a yield stress. So below the yield stress, you see this in this blue linear part. Below this is linear, and the material exhibits the elastic behavior, as I said. So all the deformations will be reversible. And beyond the yield point, the material undergoes the plastic deformation. Plastic means a permanent or a reversible change. Comparing these material behaviors with the definitions of limit load and ultimate load, you can actually infer that the limit load should remain below the yield point. Okay, here it's a yield point. While the ultimate load should be below the maximum load capacity of the material. So in the case of composites, you see the green ones, the composites, which remain elastic until failure or fracture, the ultimate load should be below the failure load. So, presently, the safety factors employed for composites tend to be higher than those for metal alloys. And this is because the fracture loads of composites exhibit more variability or scatter, mm, which is which is at the greater margin of safety in the design. In the mid 1950s, the Dutch aircraft manufacturer Fokker uh, announced its latest aircraft, the Fokker F-27, as you see in here. This is Fokker F-27 Friendship. And this aircraft had several innovative features, including uh, metal bonded structures, early use of composite parts, and a pressurized cabin. So the incorporation of a pressure cabin was very crucial at that time for flying at high altitudes, particularly above 10,000 feet or 3 kilometers altitude, where at that altitude the air becomes very thin and you cannot easily breathe. So many new aircraft during this era were equipped with pressure cabins to facilitate high altitude flight, where, as I said, the air density is very low. So the introduction of pressure cabins, along with the emergence of jet engines shortly after the Second World War, revolutionized the air travel by enabling faster and also longer distance flights. So this development marked a significant advancement in aviation and greatly enhanced the accessibility and efficiency of air travel. The introduction of a pressure cabin in aircraft also introduced new forces acting on the skin of the aircraft. So, if you remember in our previous discussion, we learned that the metal skin of an aircraft carries the load, and with the addition of a pressure cabin, the skin experiences even much more greater loading. And in the calculation presented on this slide, we focus on the circumferential stress, also known as the hoop stress. If you assume that the half cylinder has a length of 1 meter and the thickness of this is actually t, small t, and the radius as is shown in here is r. We consider the pressure inside the cylinder as P2 and the pressure outside is P1. So um, the pressure difference delta P is P2 minus P1. And okay, this aircraft, this cabin is at equilibrium. So to maintain this equilibrium, the downward force must be equal to the upward force. So why we are not talking about the side forces, because this is a cylinder, so it's symmetric, and side forces to the left and right will cancel each other. So in this scenario, twice the hoop stress, 2 times sigma times the thickness, should be equal to the integral of the pressure difference over the half cylinder. So through some manipulation, you can derive a simple formula which says that the hoop or circumferential stress, sigma circumferential, equals the pressure difference multiplied by the radius of the cylinder and divided by the thickness of the skin. So since pressure acts uniformly in all directions, there is also a longitudinal force or a stress exerted on the fuselage skin. This stress can be readily calculated using the following illustration. When a simple disc serves as the end cap or bulkhead of the cylinder, the calculation is pretty straightforward. So the pressure force to the right equals the pressure difference multiplied by the area of the disc. So the opposing force is borne by the skin, which in this case equates to stress multiplied by the circumference of the fuselage and the thickness of the skin. So through some manipulation again of these formulas, you can derive the longitudinal stress in the skin, sigma longitudinal, which is half of the magnitude of the circumferential or hoop stress. So this is a very important result. The circumferential stress is twice the longitudinal stress. So to show you some give you some idea about the magnitude of the stresses, let's consider this example. Imagine that you are flying in a very small aircraft, and this aircraft is designed for 50 to 100 passengers, and the fuselage diameter is 4 meters, so the radius will be 2 meters of the fuselage. And if this aircraft is flying at altitude of 11,000 meters, again you can refer to the international standard atmosphere, you can calculate the outside pressure using the formulas you remember, and it will result in slightly over 22 kilopascal, 22,620 pascals. So the pressure inside the cabin, in this example, it is said that will be maintained at nearly 71 or 70% of the sea level. And with these values, you can calculate the pressure difference. So delta P, P2 minus P1. And if you use the radius and pressure difference, you can find the stress times the thickness of the skin is 96 over 96,000 Newton per meter for the hoop stress, circumferential stress, and actually half of that, which is 48,308 Newton per meters for the longitudinal stress. And depending on the thickness of the skin, you can obtain different values for the hoop and longitudinal stresses. For instance, with skin thickness of 1 millimeter, the hoop stress is nearly 100 uh, meganewtons per meter, or 100 newtons per square millimeter, while with the thickness of 2 millimeters, it means that if you double the thickness, it will be dropped to nearly 50. So it's worth noting that the maximum allowable stress for metal skins is typically around 100, and these stresses result solely from the pressurization load cases. So in reality, you have other loads such as bending or torsion moments, and these further affect the stress distribution in the aircraft structure. Indeed, the calculations we've conducted uh, so far have been based on the assumption of undisturbed cylindrical fuselages. However, in reality, aircraft fuselages feature numerous cutouts for windows, doors, hatches, and other components, and each cutout introduces a stress concentration, leading to higher local stresses in the vicinity of the openings and stuff. So to ensure that the overall stresses in the fuselage skin remain below the maximum allowable value, the local reinforcements will be necessary, and it typically involves increasing the thickness of the skin in the areas surrounding the cutouts. By reinforcing these regions, the structural integrity of the fuselage is maintained, and it will actually avoid the risk of failure due to elevated stresses caused by the presence of cutouts. The pressure cabins are also closely linked to metal fatigue, as uh, demonstrated by the case of the British de Havilland Comet, the first operational jet aircraft of the post-World War, Second World War. And in the early 1950s, two of these aircraft tragically crashed, leaving investigators puzzled as to the cause. And subsequent thorough investigations revealed that the metal fatigue in rectangular shapes was the root cause of these accidents. And until then, the significance of metal fatigue was underestimated. Unfortunately, certain design choices made in the construction of the comets led to fatigue and subsequent failure of the fuselage structure during flight. So it is again highlighting the critical importance of considering metal fatigue in the design and maintenance of aircraft structures, particularly those equipped with pressure cabins, which are operating at high altitude flight. So in here we have a video from National Geographic uh, channel, and it is actually showing the disaster happened in the comet's failure. So let's watch it together.
10:31 a.m., January 10th, 1954. 26 minutes to disaster. Flight 781 takes off from Rome Airport. The plane is designed with an exceptionally thin aluminium skin. Rivets punched into the aircraft during construction create microscopic manufacturing defects. On each flight, the pressurization system puts enormous strain on the fuselage, causing stress to the skin, especially around the windows and doors. Repeated pressurizations turn the manufacturing defects into fatigue cracks that get bigger with every flight. 19 minutes to disaster. Flight 781 climbs to 11,000 meters. As it ascends, the pressure increases and the aircraft's skin becomes more stressed. At 10:51 a.m., the Comet's pilot, Captain Gibson, sends a radio message. 5 seconds to disaster. A fatigue crack reaches 2 centimeters in length, and the aircraft's skin rips apart. At 10:57 a.m., the shattered pieces of Flight 781 fall from the sky. 35 people are dead.
So, metal fatigue is similar to the experience of bending a paper clip. You see the paper clips here. Uh, due to uh, if you get a paper clip and bend it back and forth until it breaks, it shows you actually a metal fatigue. Even though a paper clip might be very strong enough to tolerate a single force with bending force, it can eventually break from repeated bending. And similarly, metal fatigue occurs in materials when they are subjected to repetitive loading and unloading. And this repetitive loading can be much smaller than the force needed to cause immediate failure in the material. And in the case of aircraft, metal fatigue often occurs in components such as the fuselage, which is pressurized during each flight and then unpressurized when the aircraft descends and lands. And it could happen in the wings, especially when the aircraft encounters turbulence. The wing is oscillating, going up and down. So it is a repetitive uh, forcing. And over time, these repeated cycles of loading and unloading can lead to the development of cracks and ultimately failure in the metal structure. So this graph displays what's known as a SN curve for an aluminum alloy. The horizontal axis represents the number of cycles logarithmically, while you have this vertical axis showing the failure stress. So at the onset, during a static test, the material fails at a stress of 320 megapascal, this point. And as the number of cycles increases, the failure stress decreases. For instance, at um, 100 cycles, where is it? This is 100 cycles. Uh, the failure stresses drops to almost 260 megapascals. And similarly, at 1000 cycles, it decreases to 200 megapascal. And if you see the 10,000 cycles, it is again reduced to near 160 megapascals and so on. So these patterns mirrors of the observations from the paperclip As the number of repetitive loads increases, the maximum applicable load decreases. And this phenomenon again shows the importance of considering fatigue effects in materials subjected to cyclic loading, such as those experienced by aircraft components during the flight. Fatigue in metals often manifests as visible cracks in the sheets, typically originating at stress concentrations. So those points are like notches or rivet holes. The process of crack formation begins with an initial period. This is the initial period, and during which um, some time is required for a crack to start. And once initiated, the crack undergoes a growth period. So it's growing, and it's gradually extending. So this figure illustrates the relationship between the number of cycles and the length of the crack. And initially, there is a delay before the crack becomes visible, and this is known as the initiation period. And during this phase, the crack remains very small and you cannot detect it, it is undetectable. However, you can use specialized equipment to detect the cracks at any early stage as well. So once the crack becomes visible, it begins to grow exponentially. And if it is left unchecked, the crack will continue to propagate until it reaches a critical size, leading to the structural or the component failure. So to prevent such failures, frequent inspections of components are necessary, and when the crack is detected, the components must be repaired promptly. So in an ideal scenario, cracked components are inspected multiple times before the crack reaches critical dimensions. And this allows for timely repairs and preventing those catastrophic failures as you saw as an example of that in comets. Uh, so actually typical loads that can induce fatigue in aircraft structures include various factors such as uh, wing loads. So these loads result from aerodynamic forces experienced during the maneuvers, like the turn and roll, as well as takeoff and landing. It could be forces introduced by flaps or engines, the thrust force. So when flaps are deployed during takeoff and landing to increase the lift, these are the additional forces, and while engines generate thrust forces to propel the aircraft forward, these forces can impose additional stress on the aircraft structure. And you can have the fuselage pressurization cycle, the cycle pressurization and the depressurization of the fuselage during flight are significant factors contributing to the fatigue. And the repeated pressurization and the depressurization cycles can lead to stress accumulation and fatigue damage in the fuselage structure. Also, you can have loads transferred by the wings and tail section. Uh, the wings and tail section of the aircraft also experience various aerodynamic loads during the flight, and these are transmitted to the fuselage and other structural components and can contribute to the overall fatigue. So overall, these loads play a critical role in the fatigue life of aircraft structures and must be carefully considered in design and maintenance and also inspection processes to ensure the structural integrity and safety of the aircraft. So with this, we can finish the structure part, and I'll see you soon in the next lecture. Take care and have a good day.